Hello, I'm here to talk to you about light right now. Light, right? Woo, cool. This is a laser light. This gives off a form of light. You've seen it before. I've called it monochromatic, meaning it's all the same color. And I've called it coherent, meaning it's all going in the same direction. But there's lots of different kinds of light, as we're going to see in our classroom experiences. You have light that is made up of many different colors of light. In fact, light is part of what we would call the electromagnetic spectrum. And light is what is called electromagnetic radiation. Now there's some debate, I guess, among astronomers and physicists. I tend to call all forms of electromagnetic radiation light, but sometimes some physicists only call visible light light. And the physics regents exams, for example, will only call visible forms of light light, and the rest of it they'll call electromagnetic radiation. But it's all essentially the same thing, the same kind of wave, just the frequency is different. So what we find is that there are many visible and invisible parts to the electromagnetic spectrum. This includes visible light, red, green, blue, orange, yellow, violet. It also includes non-visible parts, such as X-rays, gamma rays, microwave rays, radio waves, etc., etc. And you can find many of these on the reference table, and we'll go over them in class as well. Ultimately, though, no matter what kind of light you're dealing with or electromagnetic radiation, there are similarities, like they are all transverse waves, meaning that if the wave is moving to the right, it's vibrating perpendicular to it. Transverse vibrations are perpendicular to the direction of motion. The frequency of electromagnetic radiation determines the color. And what we find is that blue, and you can get this off the reference table too, but blue has a high frequency. And because it has a high frequency, and frequency and wavelength are related, it has a low or a long wavelength. I'm going to change low to long. So as frequency goes up, wavelength goes down on a long wavelength. This is different than red, which is at the opposite side of the visible spectrum. Red has a... Ooh, is that turning this off? Red has a low frequency and a short wavelength. However, regardless of the color of light, what we find is that in a vacuum, all light travels at exactly the same speed, which goes by the letter c, which is 3 times 10 to the 8th meters per second. So no matter what color of light it is, no matter how much energy it has, it all goes at the same speed in a vacuum. This is not true when it passes through materials like glass. Some things slow down more than others. But in a vacuum, it all travels at the same speed. We also find that frequency is related to energy. So the higher the frequency, the higher the energy of the wave. I'm about to erase this, so feel free to pause and make any, write down anything you want. I do want to get back to color a little bit more. So if we look at the different colors of light, and I said frequency is related to color, if light travels through a material, in a material like glass, the color doesn't change. So your frequency stays the same. However, the light does slow down, and we're going to get to this in a future video too. It slows down, and if it slows down and we know the speed of light is equal to frequency times wavelength, that means if the frequency stays the same, the light's wavelength has got to change. and it would have to basically decrease. So if the velocity decreases, the right side's also got to decrease as well. And we're going to look at certain things like what happens when we go through a material. These are terms like reflection and refraction in a future video. One other term I do want to introduce in this video is the term dispersion. So white light often has many colors to it. And we can look at with the prism and see that red light, green light, blue light, etc., all make up white light. But you can also see the term dispersion, and that would be like sending white light through a prism. Dispersion separates the colors of light. And it's essentially because as you go through a material, the speed of light slows down when it goes through glass, and it doesn't all slow down at the same rate. So because it doesn't slow down at the same rate, the light bends at different angles depending on the color of the light. So you get this effect called dispersion, where you can separate the colors of light. There's a lot more to light. We could get into it in future videos and in class. But for now, I want to thank you very much for watching. I'm going to stand on the way in case you wanted to write that down too. Thank you for watching.